for all of you still attending today's class. So Dr. Muhammad suggests that we should end this today's lecture plus lab earlier. So I decided to rearrange a little bit so we can end it before 12 o'clock. Is that good for you? Okay. So before we start the class, I would like to tell you that I'm very honored to have the chance to get along with you for the 5 days in the workshop. So I feel that you are very talented students, and the graduates also. My teaching assistant treat me very well. So I'm very happy to be here with you. So I don't want this to be just 5 days. So I know that you may still have lots of questions, lots of problems, and you may be interested in solar cells in the future. So I would like to leave my contact information. So if you have any problem, just let me know. If you think that I can be of any help in any aspect, just do not hesitate to contact me. As I said earlier, we are the world, we're a family. So we should help each other. So if you are interested in solar cell, just let me know. Just let me know. And I also would also like to encourage you, if you have the funding or you are free to go abroad to study, then please choose our university. And if possible, choose me as your advisor. Then I will be more than happy to take care of you. Actually, I like the students here. I like the environment, and I like the food here. And like my hotel, very beautiful. Someone just challenged me. How about the weather? Okay, okay, a little bit hot. But somehow it has an advantage because I found out I didn't sweat. Because back in Taiwan, even though the temperature is not as high as here, yeah, you will feel sweat. You will feel very, the humidity is much higher than here. So even though the temperature is higher, I feel more comfortable here. So I quite fit in here. And also I'm not enjoying drink alcohol. So that make me fit in here. So just let you know that if you have a chance to go abroad, and if you are you're trying to develop your career in this industry, just let me know. If you go to Taiwan, just try to contact me. I probably will take you to visit the companies that making solar cell and solar modules. All right. And also, if you want to pursue higher degree, for example, if you want to go to Europe, and if you want to go to the United States for further high degree pursue, usually you need to develop your credit, your academic credit. That is by the publication, doing research and publication. Usually we have a lot of foreign students thinking about this way. So they first come to Taiwan, we'll train them to study certain topics. So they will publish paper and establish their credit. Then immediately they will be accepted by very good university, world-class level universities. So you may consider Taiwan as your middle point between in your career development, academic career development. If you are interested in career, not only career, but also not only academic career, but also the job opportunity. If you want to really interested in that, in this field, then you should go to Taiwan to take a look, right? Okay, so this is my email. And This is our university. I got the photo. I noticed that I have a photo for our university that in the file that I presented yesterday. This is a place, that's our campus. Yeah, so very different, right? Very different. But we are too many waters, too humid, maybe for you. But no problem. You can stay at the lab, stay at the clean room. Then we have air condition, so so you will feel comfortable. So don't worry about that. Okay, so I also need to say something about yesterday's desensitized solar cell. Okay, so this will be the desensitized solar cell that you assembled yesterday. I was expecting that the voltage should be 0.0 something in this order, voltage in this order. But somehow I noticed some group that has voltage goes to 0.36 something. Which group? Can you raise your hand? Oh, your group, right? Huh? 3.5. That is because you series connected it. No, I'm not talking. I'm talking about specific. Just one piece. Well, really? I don't believe you. Yes. Are they? So some of you really did the solar cell with very high voltage then, because usually the solar cell voltage, like the output, actually the VOC will be around 0.6 or 0.7 volts.
Maybe he means 0.0.
Yeah, I'm not sure, but I noticed because someone told me, and someone told me we already got 0.36 or something. Is that correct? Yeah. Okay, so do you have the picture that taken by someone to confirm that your reading is correct? University, they took picture, or maybe, yeah, it's if possible, could I be able to receive that photos? Because this is something that I didn't know before. You must do something very special to make this happen. And how this can happen, I don't know. But at least it tells you there's a possibility of only using this kind of material, then we'll be able to make solar cell with this high voltage. All right? So this is a topic worth study, how you can refine your process and get a good value. But because usually if you don't do this carefully or without any direction, if you just prepare, then you won't get this high voltage. There must be something you accidentally got it, so you got high voltage. Okay, so yes?
What's the lifetime for this?
For the solar cell that you made yesterday, it probably will last a few days because you need to have a liquid electrolyte. So when the electrolyte is dry, then you won't be able to get. You need to refill the iodine solution.
But the actual one, what you did?
The actual one will still be 10 years, 20 years, because they use, excuse me? Do you have? Yes. Can you send it to me through email? Okay. Just like to show the photos under the illumination and without the illumination, so have a comparison. So I will put your photos, the photo that you send me, to the file that I'm going to present to the student back in Taiwan. All right, and I'll mention If you can put your name, then I will, or your group, then I will mention about you that you did this result. It's not me, that's your contribution. All right? So did you do anything different? Oh, I haven't replied your question yet. So for the electrolyte solution, then you need to have to seal it so that electrolyte will not leak or evaporate. You leave it, and it's not being oxidized. Oxygen cannot go inside because if oxygen goes inside, the dye will change its chemical composition, and eventually you will have failure. So seal is a very important issue. However, the technology for sealing the solar cell is not new. It's already been done for quite long. So because nowadays we are using television, not like this, but use liquid crystal, right? So if you are not sealing it correctly, then you are going to be using the television for maybe 1 week. That's all. Maybe 1 day. They are liquid. The liquid are liquid. So usually nowadays our television can use more than 10 years. I don't know. Do you have your television use liquid crystal? I believe so. Nowadays you are always using that big screen. So, and you are still using it for years. So that means the sealing is not a problem. Also nowadays they are using gel state electrolyte. So it's not liquid anymore, like solid. So it illuminates or mitigates this problem furthermore. All right, so this kind of technology this solar cell can last for very long then. All right, so I'll move back to the previous question. What do you think you did differently for that special solar cell which give you very high voltage? Could you remind yourself, think about yourself, what did you do for that certain kind of that certain piece of solar cell differently than the other solar cell? Sorry? Accuracy?
The day.
In terms of what?
Doing the steps.
The steps. But you did all the cell with the same steps, right? Yeah, I try to figure out, really, because this is something I didn't know, because usually if we didn't do that, usually if you follow the process, then we will get the voltage not that high, because we are using the dye not specifically designed for the decentralized solar cell. We are using vegetable juices for that purpose. So it shouldn't give you the solar cell with that high solar efficiency. That is what I'm going to tell you why the dye, what we need to concern about the choice of the dye. Is this the structure? Do you are familiar with the structure yet? Yes. From the top, yesterday, this is ITO glass. We put titanium oxide, we spray the titanium oxide on top and put to the furnace oven for baking for half hour. So it will stick, now it will stick on ITO. All right, and this is porous. Since we are not heating, so it's not densely sintered. So there is porous structure, so we'll be able to absorb a lot of dye. So if you dip the dye on titanium oxide, it will be absorbed inside the porous structure. Then instead of putting this layer, we try to prepare the counter electrode. And for counter electrode, we are not using platinum because platinum is too expensive for our experiment. So instead of using platinum, we use graphite. So we kind of bake the glass on the candle, in the flame of a candle, so they can The carbon can be deposited. And of course, there's a lot of graphite for conducting purpose. The reason why we need this is because we want to increase the surface area. Increase the surface area as much as possible so that the carrier exchange will occur much faster in this interface. Then it will increase the reaction of the ion. So it will lead the reduction of the resistance in this phase. And in turn, it will increase the efficiency. So every step has some function about increasing the efficiency of solar cell. We want all the reaction be very fast. Then it will reduce the internal resistance. As I said earlier, yesterday, the series resistance. All this internal resistance may contribute to the total series resistance of the solar cell. So you want to have this surface area as large as possible so that the charge transfer across the interface is fast. Okay, then after we clamp these two electrode together, then we inject the inject the electrolyte solution. That is iodine solution. Then we finish the process. All right. So now today, if I repeat this, then you will feel more solid about the idea. Now, so I'm going to talk about the theory, operation principles. You might not pay attention to these slides yesterday because at that time you still have no idea about how to make that sensitized solar cell. But now it's a good time for me to explain this again. This is indium tin oxide, and this is titanium oxide layer. And actually, dye is sitting inside the titanium oxide. But for schematic purpose, I just put here. All right, it's on top of the titanium oxide layer, then followed by the electrode layer, then the counter electrode layer. Okay, so as I told you earlier, titanium has very wide band gap. This is the conduction band edge of titanium oxide. This is valence band of titanium oxide. And the band gap is about 3.3 or 3.2 eV. All right, so it's very wide because so it is already in the ultraviolet region. If you want to excite titanium oxide to make electron and holes, you can only use ultraviolet light. All right, but ultraviolet light is minimal. It's occupy only very small portions in the whole solar spectrum. As I showed you yesterday, they only occupy probably 5% of the whole solar spectrum. So if you are going to use the sun as an energy source for this kind of solar cell for activate titanium oxide, it's not going to give you very high conversion efficiency then. However, if you put the dye on top of it, this dye will absorb the visible light for titanium oxide. Okay, so this is not p-n junction anymore. This is called dye sensitized solar cell. The dye will absorb. You can choose the dye so that it can absorb the energy that titanium oxide cannot absorb. So you use this dye. Dye is not semiconductor, it's molecule. So for conventional dye sensitized solar cell, it's not semiconductor. So this is not the conduction band edge, and this is not the valence band edge. This is just we call the LUMO or HOMO. Okay. So simplify. Sometimes we call LUMO and HOMO, and these are the energy level of the molecules. We can use molecule to absorb the light for us. All right. So you carefully choose the energy level of the molecules, so it can absorb different color of light. So actually, for dye-sensitized solar cell, it can have different colors, and it can be transparent to the light, because you can design the dye or choose the dye so that it's still transparent, but with color. All right. So that's the function of dye. When dye absorbs electrons, it absorbs photon, it will excite the electron from HOMO. HOMO means highest orbital of molecular orbital. And this LUMO is lowest unoccupied molecular orbital. This is highest occupied molecular orbital. So electron is here, but there's no electron in this level. So if it absorbs light, then it will excite the electron from the HOMO to LUMO, right? So then you can choose whatever you want. Usually the band gap will be somewhere around 1.1 EV or 1.0 EV. Then you will get, you cannot shrink this band gap, oh no, the exciting level, the difference between of energy excitation, too small. You cannot choose small. If you choose too small, then there will be no voltage output. No voltage output. It's very difficult to get the voltage output, because the voltage energy here and the energy on the other side should still fall in between HOMO and LUMO of the dye. So you cannot choose this distance too small. All right? So after you absorb the light, the electron is here. And since this layer should be higher than the conduction band of titanium dioxide, so it will have very big chance to go to the left. All right? And for the holes created here, because once the electron got excited, they're leaving an empty orbital. So this is called hole also. The hole cannot go this way because there's no orbital in titanium dioxide in between the band gap. So hole cannot go this way. So the only choice for the hole is going this way. Even though the electron can go either left or right, but the chance is equal. So half of electron may go this side, but for hole can only go to the right. So you still generate electron and holes with certain level difference. All right? So it will accomplish excitation circle. This hole will go through the electrolyte. Electrolyte just will take the charges to the counter electrode and being recovered here. So it accomplishes the electronic circle. Okay, so dye is very important. Not only it need to absorb as much light as possible, but one critical point is the LUMO should be always higher than titanium oxide, or at least very close to titanium oxide. Otherwise, electron will not be easy to go from dye to titanium oxide. Do you understand? If you choose the dye, some dye still has black color, but the LUMO is not located above titanium oxide. What will come out? You still got very good light absorption, but you never get an electron that can go above the conduction band of titanium oxide. Then even though you see a very black dye-sensitized solar cell, you got hardly any energy output, electrical energy output. So it's very important to choose a dye. Now, for the dye-sensitized solar cells that we made yesterday, we are just using vegetables, right? or I'm just using vegetables. So usually the vegetables, the molecules, the dye molecule inside vegetables, usually, at least in Taiwan, cannot go that high. Cannot go to that high. So they need the thermal excitation help to get the electron from the dye to the titanium oxide. That's why back in Taiwan, we never get the voltage as high as 0.036, all right? Then you told me that you get the voltage of 0.36. I'm wondering what happened, or we accidentally find some dye in that vegetable that can allow us to have high efficiency, all right? Yeah, take some back. I'm not sure if airplane allow us to take this kind of plants, live plants. I know, maybe violating the law. But yeah, I just remind you, you may have this kind of issue, that certain plant may have certain molecule that is suitable for solar cell. If you can extract this dye from that, purify that, then probably there's a chance for you to run the company. All right? I don't know. This is just for for your thinking about something that we found yesterday. Okay, I'll briefly mention about hydrogen protection. So one of the problem of solar cell is they can only produce electric power during the daytime. All right? So during the night, unless you put the solar panel inside, under the light, or not inside, under the light, then you are not going to produce electricity, especially if the light is powered by electricity. Then you just need to use the electricity directly. Don't have to use the light, then convert it to photon energy, then convert back to electric energy. Don't have to do that. So so solar cells can only produce power in the daytime. What a waste, because sometimes you still need to use electric power during the night, right? So we need to think about store it. The energy stores it so we can use later. All right, so someone just think about, we may store in the lead acid batteries. We can charge that in that batteries. But this kind of battery can only be used maybe for 1 year, 2 years, and you need to replace. If you drive the car, every time you consume a lot of materials, and it is not maybe environment protective. So someone think about this way: how about we store this energy in hydrogen as a form of hydrogen? Because if we store in hydrogen, then we can use hydrogen as a fuel. When it can activate, it can run the engines. And when hydrogen reacted with oxygen, when that is burned, what is the product of hydrogen? It's steam. So it will not harm the environment. It's a clean energy. So a lot of people think about hydrogen as a storage media, or itself as a material for energy storage for the solar cell. If we can combine the solar cell with hydrogen production, that will be a good direction. So someone think about that way. You know the electrolysis, right? Electrolysis is if you put a voltage here and put the negative side toward this, if you put the negative bias on the PT electrode, then and your electrolyte, there's a hydrogen ion or proton inside the liquid, and if you bias this negatively, the proton will receive electron in this side, in the platinum side, and become hydrogen. Okay, become hydrogen. So you'll be able to produce hydrogen. You just need to plug the power input to the wall outlet. Then you will get hydrogen. Then you just need to think about some ways to store this hydrogen. Then you can use that when night has come. Now this electric power, since solar cell is producing electric power, why don't we just use solar cell as a power source? So if we connect this to the solar cell, then we still be able to do that, all right? So this is the idea. Now there's another idea. We talk about dye-sensitized solar cell. So we know if we are going to use the solar cell structure, the solar cell don't need to even put in these places. They can put in the liquid as a solar cell. Then it can generate. All right. So for example, this can be titanium oxide. All right. This can be titanium oxide. So this is a valence band, this is conduction band. So if you give them the photon energy, it will also excite the electron from the valence band edge to the conduction band edge. All right? So you will produce an energized electron, so the level will be high, very high. So it will go to the other side and induce a reaction for the hydrogen. And even better, there's a hole here, and the hole can move to this side and have an oxidation process to produce oxygen. So you not only get hydrogen, but also you get oxygen. So you can separately store these two kinds of gases. So the solar cell does not necessarily put in here, but also you can borrow the idea from the dye-sensitized solar cell to have a structure here. Now, there's two concerns. One, titanium oxide, as I told you, this is not a very good light absorber, right? So how they can be used for light absorption? So you need to have some treatment. You need to have a dye-sensitized idea. Instead of letting titanium oxide doing his own work, you may put some dye on the surface so that it can absorb light for you.
But it will mix with the electrolyte.
However, it may react with electrolyte. So now the selection criterion is more stringent. You not only select the dye with right energy level, but you need to concern about its stability under the electrolyte. So it will not be corroded by the electrolyte itself, and it will not be harmed by the reaction happening in the electrolyte. This is one concern. You may need to use dye-sensitized idea to treat the electrode. Second, if you need to separate electron and holes, so you want the electron and hole go different ways. For example, electrons should go the other way, hole should go this way. So how? Actually, if you notice that p-n junction, there always field occurs at the junction, even though you are using the same material, silicon. If there's a difference, like p-type and n-type, when you contact them together, they'll form a junction, and there will be field across that junction. All right? Same thing happens between, for the interface between titanium oxide and electrolyte. It will form a junction, and there will be a field in this one. Okay, so depending on the matching of materials, you can design a material so that there's a field at the interface, so that when this interface illuminated, this field will force the electron to go this way, while allow holes to go the other way. So you can separate electron and holes and generate hydrogen and oxygen. Also, third problem, different energies of holes and electrons can induce different chemical reactions because the reaction has certain energy level. All right? So you need to prepare the right electron with exactly the right energy level to induce certain reaction. For example, if you are going to induce hydrogen reduction reaction, the level is here. So you should create electron energy higher than this level. If you are not going to have electron energy higher than this level, then you will not be able to help this reaction. They may be able to help the reaction, other reactions with lower energy than this one, but not this one. All right, so you need to consider the alignment. Yeah, so you need to have electrochemistry background. Some student told me that he's interested in corrosion. Actually, this electrochemistry is largely related to corrosion, not only applied to the solar cell, but also you can use like a corrosion of the steel for oil drilling or for protection. So this is another knowledge that you might be interested in. So actually we should label the reaction and find out which semiconductor is most suitable for us. So if the solution has many kinds of iron, then it will generate a lot of reactions. It's very complicated. Usually we want the electrolyte solution to be very simple. So we will not create an unwanted reaction. Okay, and also we want to wisely choose the semiconductors. So you need to have the band gap higher than this one to produce hydrogen. However, you cannot go that high. If you go that high, when electron is generated, they will fall from this one. And it will induce any possible reaction that is below this level. So before it can generate this reaction, it already induced another reaction and cannot be used for this equation. So you might end up with no hydrogen production. All right? So what will be the best semiconductor for hydrogen production? Yeah, titanium oxide. Again. So this is exactly the material that we used for, also for dye-sensitized solar cell and also for hydrogen production. You should be higher than this level, but not too high above this level. All right? And what will be another possible materials? Strontium titanium oxide and zinc oxide. Zinc oxide is a very cheap, very cost-effective material that and it's not very harmful. It's not harmful at all. You can eat. All right? So you can choose those materials. Or you may choose tungsten oxide, even though it's still lower than that, but the thermal energy will be able to help it. So this is what I want to talk to you for the hydrogen production. Okay, so for hydrogen splitting, you need to choose a semiconductor that has Eg greater than 1.8 eV. All right, so this is a separation between hydrogen reduction and the water oxidation. And not only you choose a band gap, but also you need to change the proper alignment. You need to have alignment with the edge potential with the reaction levels. All right? And you need to consider the stability of the electron so that it do not corrode it in the system, electrochemical system by the reaction. And also, we want to create as high surface area as possible to increase the reaction, to increase the contact area. Just like what we did yesterday, that we deposit the powder on that, so that it's porous structure. We want the same structure that is used for hydrogen production. Okay, so this is what I want to talk about hydrogen production. So let you think about it to see if you can. And there's one thing. If you are going to use dye to activate the semiconductor, you probably will only be able to produce hydrogen then. You're not going to be producing oxygen, because hole, then at that time, hole will be at this level. Hole will not be able to activate. Hole will go this way and combine with electron without doing any reaction. Okay, so, but doesn't matter. It doesn't matter, because if the purpose is going to produce hydrogen only, then you can use dye-sensitized idea for this purpose. And again, you need to make sure the dye is stable enough in this situation. So this is the surface area of the electrode, microstructure electrode that is made by one of my colleagues back in Taiwan. We are doing this kind of work, and they claim that the efficiency will be very high. Actually, will be very high. All right, just let you have an idea about that hydrogen production. Okay, so that's about what I'm going to talk about for the first hour. So now you can take a break for 15 minutes. Any question? Any question? Then we are going to talk about the tendon cell. I briefly mentioned in yesterday's closing ceremony keynote speech. So we'll talk about for 1 hour about the concentrated solar cell. right? Okay, let's have a break. Yes?
Excuse me, about the notes.
You want the notes, right? Actually, I think, did you get the notes that we have yesterday? We have, or the day before yesterday? Yes. Actually, I all gave it to Dr. Muhammad El Badi. So,
Is it working?
yes, it's working, but it's blinking now. It's almost,
Can I see the battery, please?
yes, it's lower. It's blinking now.
Yeah,
it's
I know.
hardly any.
I want to see the battery.
Uh-huh.
Okay.
A concentrated solar cell now. Concentrated solar cell means we concentrate the light and use that as a light source. The system will include 4 components. I jump this because we talk about this already. Here, you may need to memorize this. If you are serious about the concentrators are Fresnel lens that you see the first day with that very large plate, but very thin layer, right? It didn't look like lens, but it's actually lens. Concentrators, then multi-junction solar cell. It's a chip. That is core of this technology. You should have a very, you should have that kind of cell with tendon structure. Did all of you attend yesterday's closing ceremony? I saw that you will receive the certificate last night, but no, but not, right? Very strange. So you should actually to give you. This is the core of the technology. They will have different layers of solar cells stacked together. It's called the tendon structure. Solar trackers. Because since you are using very small chips and a very large concentrator, so you always need to confirm, make sure that the focused beam is exactly located on the chip. Because sun will move constantly. So even though you are focusing at this moment, you will not be focusing after 5 minutes. That's why for this kind of solar cell, you always need the solar trackers. Otherwise, you will not get anything. Huh? DBS?
DBS system to track the light.
To track the light. Actually, they use X direction as well, Y direction. They use different photoresistor, so they can detect the illumination difference between the two. So they will be able to feedback the results. So you will always be able to tracking the solars. And the cooling system, this might or might not be necessary. Why there's also this system? Because you are focusing the light in such a small piece. It will very hot, right? However, this kind of material can sustain high temperature. It's much, much better than silicon solar cell in terms of materials. So it can sustain. So sometimes people don't put this system, then it still can function properly. However, if you put this system, then you will have even better efficiency output. Okay. Now this is the solar cell system. You need to have, actually there are many. They are Fresnel lens the concentrators. Each piece of concentrator will respond to each one solar cell chip, the chip. And there are also a lens. This is called the first primary lens. This is called the secondary lens. It will focus. Because it's very difficult to focus to the chip, right? So it's kind of focused on this piece first. Then it will concentrate. It will guide the light to the small piece. So there will be a secondary lens. For this case, it is not focused correctly. So you can see this offset between this chip and the light, right?
Like curve, it's like curve or not?
This is curved.
Yeah, like
It's flat, but with curvatures. I'll show you the schematics. Okay. This is just for heating. We just put the chip. If you can do some things around it using some circuit, liquid circuit, then you will be able to get very high efficiency, right? Okay, so this is right alignment. If you did a good alignment with the sun, then you should get the light being focused by the Fresnel lens, so-called Fresnel lens. Then it will each piece of Fresnel lens will focus on one chip. For this case, if you have good alignment, then you don't need the secondary. You don't need secondary optics. Sometimes, if for save money, you don't use secondary. But if you use secondary, then it will collect photon, much efficient, right? But then you need to think about the cost. The more you add, the more they ask you to pay more. Okay, so it's like that. The lens, you can use a conventional lens, but we are using Fresnel lens to reduce the weight, right? So it's focus, and this is secondary optical lens, and this chip, and you should have a heat dissipate. You should consider about the heat dissipation. Okay, so this is the assembly of the structure. Okay, I'm not going to that detail. I just let you to take a look. And this will be something like this. Sorry? It's now it's this is cell itself, so it's below the second optics. All right. So this one, solar cell, and this is positive and negative. I don't know which one is positive, which one is negative, but there are two connectors for the wires, and there is a bypass diode between the between positive and negative, so that in case it's shaded or something, it can protect the solar cell. Right? Okay, this is solar cell without bypass diode protection. Okay, I will briefly go through. I will not talk about this too much detail because time limitation. Secondary optics. Okay, this is one company based in Taiwan called Thai Crystal. They are manufacturing the chips for the concentrated solar cell. You see this one? The one you see this one? This chip and the connector and the bypass diode is all here. Sorry? Dimension is about this big. This big. If you look at the PowerPoint slides, you hardly feel the dimension. You don't know the dimension. That's why we need the lab. we want you to witness the chip or the structure. Personally, you experience that, then you have more feeling, all right? Okay, so sometimes they are not doing the secondary optics, they just use this one. But if your area is really small, it's hard to focus in, then they stick one of the secondary optics on top. So you have better photon collection efficiency. Okay. Okay, so this is about this fin is cooling fin. That is about the CPU, that you can see from your computer. Yes, like this big, right? So actually this is very small, and chip is very small.
Made of aluminum.
Sorry?
Made of aluminum.
Made of
Heat sink is made of aluminum.
aluminum, I believe. Yes, aluminum. Yes. In terms of cost, that will be a good choice. But if you want to really serious about the cooling, then you need to think about something else with even higher thermal conductivity. But you know, for this kind of, previously I was thinking, because this is new technology, this one didn't have been deployed. It's still in the experimental stage, even though they're already production. The company, they were production, but it's not commonly used. All right. I noticed that in your school, SQU, you may set up one that is made in Germany, I believe. Someone told me, but I don't know where. Anybody aware that you have a concentrated solar cell in your campus? Please raise your hand. Senior, put it down. It's concentrated solar cell, not just solar panel. I'm talking about concentrated solar panel, not a regular solar panel. Yeah. How much cost? It should be almost same price as silicon, or a little bit more expensive. I should be more expensive. Otherwise, you know, it cannot compete with silicon. Otherwise, it will flourish because this efficiency is much higher.
One solar cell, that's why combined to this, we need only 6.
Huh? One solar cell.
Yeah.
This is one solar cell.
Yeah, what I mean
For the dimension.
Yeah, it's 250 watts.
Uh,
41, so we need 6.
250 watts. You need to think about, instead of looking at this, you need to look.
Yeah, as you mentioned.
Uh-huh.
The slides,
The slides?
it's 41 for each.
40 watt? Before? Where? Before? Before? This one? This is in 10,000 sun. 1,000. 1,000 sun. That is concentration is 1,000. That is, you use the area 1,000 times the chip area. Use concentrator. Then you will collect 1,000 times of the sun in one small area. Okay, because, huh? What is what? The voltage will be 2 point some eV because it is at least 3 solar cell series connected. So the voltage will add up. So it will give you very high voltage, not just 0.6. Yes?
How about the capacity of the solar?
Capacity.
Yes.
Capacity.
Like how many photons can enter?
Depend on the area of the solar cell as well as the Fresnel lens, the size of Fresnel lens. Yes. Did I give you a number of photon flux yesterday, right? like 4 times 10 to the 22nd photon per meter square per second. That is the solar flux we have. Then if we focus that by 100 times, that will be the flux absorbed by the concentrated solar cell. Right? This solar cell is very expensive. It's very expensive. So we cannot deploy this kind of solar cell as like large area. Right? Like silicon, we cannot do that because it's 10 times, maybe 100 times very more expensive than silicon. However, we can use smaller one. We cut it into smaller pieces. Instead of deploy that using large area, we use concentrated lens to collect the same energy per area into that small chip. So we can save a lot of money, even though the chip is very expensive.
So this solar cell, it will produce same large.
We can produce that same with large area as well. And efficiency will definitely higher than silicon. But it's very expensive.
Yes, but I mean, if we compare with the silicon cell.
It will be high efficient, much higher efficiency than silicon. But for example, you have...
Efficiency per area, you mean?
Yes. Efficiency per area is larger than silicon. It's larger than silicon, yes. But it may, so for example, solar cell, silicon solar cell efficiency is like 20%. And this kind of solar cell, the efficiency is 40%. 2 times of the silicon solar cell efficiency, all right? But how much will you pay for this kind of solar cell? You need to pay 100 times, 100, maybe 1,000 times of the price of silicon. So which one will you choose? So, yeah, sure, it's no second word, silicon. So how to solve this problem? How to compete with silicon technology? Instead of deploy it in the large area, even though it gives you twice the efficiency, but it costs you 2,000 times of the cost. So instead of using that as flat panel, you cut it into small pieces, 1,000 times smaller. So you can save a lot of money. You can reduce the price 1,000 times. But in the meantime, you still collect the same area of photons and concentrate in this chip. So you still get the same flux in terms of that large area of the Fresnel lens. Then, even better, if you focus, the efficiency of that chip increases because your concentration. So you can reduce the price to the level about the same price as silicon technology, while you are increasing its efficiency furthermore. So this is the base of this kind of technology, even though the chip is very expensive, right? So it needs to use concentration. Yes?
Why is it expensive in terms of material?
Because it's going to do so-called the tendon structure. Tendon structure is the structure that they stack maybe 3 layers, 3 p-n junctions together. So it involves a growth of crystals, so-called epithelial growth of those layers.
Fabrication process.
Huh?
Fabrication process.
Fabrication process. So it's very difficult to align those 3 p-n junctions in terms of production, even though the idea is very simple, right? As I told you yesterday. But the fabrication is another problem. Fabrication itself requires knowledge. Okay. Any other question? Any other question? Since we are not going through all the detail, I think it's good for you to just raise your question. Yes?
Well, before, earlier you showed us a slide where there were opposite of the light.
Sorry?
photo where there was an offset of the.
Offset, yes.
Yeah, why is it supposed to would it
It will cause trouble. It will cause trouble if you are, because it is not aligned to the sun. So you need to track the sun so that the light here will focus on, at least on the secondary optics. Offset, because we turn off the tracker at this moment when we take a picture. I took this picture by myself, so I know what happened. It's not a function. We intended to let it stop. So, and after a certain period of time, the focal point just moved to somewhere place. This is for experiment purpose, right? Okay, so for the Fresnel lens, the idea is very simple. You want to make lens, then you need to have a curvature. Then it's bulky, it's heavy. Since you are going to tilt, you are going to track the sun. You want to keep the system as light as possible. So it's easy for you to drive, to control. So instead of using conventional lens, is there any way that we can reduce weight while keeping the curvature on the surface, right? So we just cut this into several pieces and remain the curvature on the surface. Then you will still be able to focus that while reduce the volume of the lens, right? Okay, so this idea is not new because you know the light tower. How do you know the light? You see, you sail in the sea. You need to have those light, right? Use this one because you need to turn around to move. So they don't want to be very heavy. So you use this structure, so it can project light to very far away while keeping it, the weight very low, right? And also your car. If you take a look of the light of the car, it may apply this kind of technology as well. But you know, since there's zigzag, so this magnification is for projecting the light only. You are not going to use this structure for microscopic observation because there's still scattering at those boundaries. So you will not be able to see very clear images. This structure is only good for projecting the light while reducing its weight, but it's not for imaging.
It will be same efficiency.
Efficiency, about the same. Efficiency, almost the same. But it's not good for imaging. You lose a lot of detail. So it cannot be used in the telescope or microscope.
It will be not clear.
Yes. So even though we have this kind of structure, this is only for projection of light, or focusing the light, not for imaging. Okay, this is a dissection of structure. So things make this figure is more clear how to make this, right? Then you can use just a lace to scribe in circles. Just turn around, you will be able to get this kind of. Do the machining, they will be able to make this kind of lens, called Fresnel lens. Okay. Fresnel lens, specialty, low cost, low weight, being generally available, equivalent to plano-convex lens. Spherical aberration can be reduced. There are good things because you reduce the thickness of lens. So some effect called spherical aberration can be removed by this design. Spherical aberration occurs when you very thick, different thickness of the lens. So there are still pathways inside the lens. That will cause you some trouble. But if you make this lens as a Fresnel structure, so there is the same thickness everywhere, almost same thickness everywhere. So you can use very easy way to reduce the spherical aberration. Okay, they can be used for collimating the beams of light, intercepting focusing light from a distant source onto optical detector. Okay, but there's limitation. As I told you earlier, it can be used for imaging. This is what you need to know. The only thing that you need to know about the disadvantage of the Fresnel lens. Okay, so this is some place I want to spend more time to you about the tandem solar cell, right? See, this is the solar spectrum. Now you are more familiar with that because I've repeated this several times, right? So what will be the UV located? Where will be the UV located in the spectrum? The UV is a photon with wavelengths shorter than 400 nanometer. All right, so it will be below this region, right? UV or even go to X-ray here. So it compared with the whole spectrum of the sun, it only occupies about 5%, or some say 3%. So is there a lot of photons in terms of percentage of UV in solar spectrum? No, only a little bit. But how we feel, why sometimes we feel there's a lot of UV in the sun? That is because each photon, the UV photon, has high energy. Each particle, each photon has high energy, but the number is very small. So it will still harm our skin. Actually, X-ray is very powerful. Its energy can break the chemical bonds of the material in the world, so including our skin, of course. So it will break the bond, and your skin is destroyed. Then you will get the cancer, skin cancer, if you are not protecting yourself. So, but actually its number, in terms of number, is very low in the whole spectrum of the solar spectrum. Now, you can convert this axis into photon energy. Can you? Yes. Can you convert the axis from wavelength to photon energy? Yes, because E equal to h mu, right? Mu is the frequency, electromagnetic wave, frequency of electromagnetic wave. So mu equals to C over lambda, yes. So you know C, 3 times 10 to the 8th meter per second. Then you just need to plug in the lambda. You'll be able to get the photon energy. So you can convert this one, this axis, to this axis, okay? Now also, you can convert this y-axis to this y-axis. This x-axis, this y-axis is the spectral irradiance. Spectral irradiance is like energy, the power per unit area, or the energy per unit area per second, per unit time. So this is energy, in terms of energy. This is in terms of photon flux, like how many meters, how many current will you produce per unit area. And the current is related to the number of photons per second. Number of charges passed through per second. It's not related to energy. So you need to convert the energy to number of photons. Do you know how to convert that? The same equation. Different photon with different wavelengths will have different energy. So you can convert the energy to number of photons for different photons energies. So you will be able to convert this y-axis. This is energy to numbers. It's like flux. Flux, because current is actually the flux times the charge. Unit charge. The charge is 1.6 times 10 to the minus 19, right? Coulomb. Okay, so you can easily do the conversion from energy to number flux, energy flux to number flux. So once you get this curvature, you will be easy to convert this from left to the right. It's possible. You don't have to do it by yourself. Someone already did that for you. Here. Now, I repeat this diagram shown here. All right? So I want to know in unit area, in unit time, what is the irradiation? What is the number of photons that will irradiate on our solar panel? So, and I want to know all the number of photons, not just the UV or not the infrared, everything. So, if I want to know the total number, the photon flux, then what I need to do is just integrate this curve, then we'll be able to get that. So I integrate from energy is very high, which is hardly any photon with this high energy. Let's just go to X-ray already. So hardly any photon, then I just integrate. Actually, I get this area gradually, right? So this curve is actually the integration of the area. The more you integrate from high energy to low energy, the higher the number of the flux. Eventually, you will get a number around here, 4 times 10 to the 21st number of photons that you can receive per meter square per second. That is the flux you have. And these photons can be large with large energy like UV, can be small energy like infrared. Regardless, I want to collect everything. Then this is the number, all the photons, number of photons that I can receive. Okay, so if you want to make the solar cell with only one p-n junction, then you need to wisely choose your band gap. For example, if you choose the band gap like 1.4, then you can absorb the light with energy larger than 1.4 to create electrons and holes. Do you understand? You can, for this kind of semiconductor, it will absorb light with energy equal to or greater than 1.4 eV. Okay. Then it will create electron with energy at the conduction band edge, which is 1.4 eV. Then when they recombine with holes, they will produce this large energy, exactly equivalent to the area shown here. All right? Then what about those energies higher than the band gap, 1.4 eV? those are dissipated through the thermalization process. Dissipated. It's not only dissipated, it creates thermal problem because you hit your solar cell. So your solar cell efficiency drops, your VOC drops. So this is the problem. This area, triangle, is not going to be used by this solar cell. Okay?
So as much you minimize that area is much better.
Yes. Yes. Of course. Now, but if you want to minimize this area, can you choose a semiconductor with bigger band gap so you can reduce the thermal problem? Can you? Of course you can. But again, there is another triangle. You increase the triangle. This part of the triangle is the photon energy that has photon energy less than your band gap. Less than your band gap. So this kind of photon will just penetrate through your semiconductor without being absorbed by the semiconductor. So it is transparent to your semiconductor. It's not going to be absorbed. So for photon energy with less than the band gap of the semiconductor you choose for the solar cell, this triangle, this area, the energy representing this area, is not going to be used for the solar cell. Yes?
Can we use heat sink passive?
Huh?
Passive heat sink.
Passive heat sink.
Without,
Yes, for passive heat sink, yes. But what do you try to solve? Yes, you can reduce the temperature. That's all right. That's very good. But still, you cannot use the energy here. You just prevent the thermal effect for the solar cell. But you cannot take advantage or use the energy represented by this triangle. Right? Still, you cannot use. Right? So you solve portion of the problem, but not the majority of the problem that I'm going to mention here. You are not going to be using this area and this area. You will be only using this area. All right? So if we are going to use one PN junction to make the highest power output, you basically just choose points along these curves that give you the highest area of this rectangle. Okay? Understand? Understand? This is very important. Maybe I talked 3 times already, maybe, but you probably only be able to understand now. All right? That's why I want to spend more time today. Sorry? Okay, I've already passed the time. Okay, maybe 5 more minutes, all right? Okay, this is only the area that we can use by single PN junction. So again, if we can use 3 solar cells, then we can reduce those triangles. Those are triangles that the energy that we cannot use. So if we can stack 3 solar cells, or maybe stack 4 or 5 solar cells, we can reduce dissipation or the waste of energy. And can you?
Do more than 3.
Sure. But you need to pay back.
yeah, of course.
Pay back the things that you did here. Okay, so the idea is using 3 PN junction, right? And absorb different light, different portions of photon energies, right?
Same area, different area.
Oh yeah, because I already told you yesterday. Now you know. Okay, it's just like this one, right? This is a very smart design. Very smart design. I cannot think about this. They use the band gap, wide band gap, from around the 1.8, say, 1.8. So it can absorb light with photon energy greater than 1.8. Right? And what are about those energy, photon energies lower than 1.8 eV? They will be transparent and penetrate through. They will not be absorbed by this layer. So it will not be consumed on the first layer. Then, but when they go in this second layer, they will be absorbed by this layer. This material has a band gap around 1.3 or 1.4. So now there's only energy remaining for those, the only photon remaining for those energy lower than 1.7, right? Going to second layer. Then got absorbed by the second layer, all the way to the energy at 1.3 eV. Okay? Then for those energy lower than, for those photon energy lower than 1.3 eV, they are still transparent to this layer. Then they're going back to the third one, the bottom layer. All right, and got absorbed by here. So this can be continuous done. Even you know this structure, if you only use 3 layers, then you will increase the efficiency. Then you can increase further layers. Then you can further increase the efficiency. All right? But the problem is the process of this is difficult. It is expensive. However, we have company in Taiwan know how to do this. It may not be that difficult. You know, we'll say it's very difficult, but for them it's very easy. So if you enter the company, you will know the secret, you will know the detail. All right? I don't know because I'm not working for them.
Can we visit this company?
Sorry?
Can we visit this company here in Taiwan?
Oh yes, sure. You contact me, I'll bring you to there. Okay, I think because of time limitation, I should finish my lecture here. Okay, thank you very much for attending the workshop from the first day.
عبد الرحمن سعيد المسكري.
عبد الرحيم
سوري عفوا. عبد الرحيم. محمد الهلائي. حسن محمد اليافعي. محمد سعيد سرور. سالم غانم اليعقوبي. مريم خليفة السناني. هاجر يعقوب الجابري. خميس محمد الزعابي. عامر سيف الهنائي. ملا بليز ويلكم. مازن سيف الحسني. بسنا سيف. مالك محمد اللباني. الصلت سليمان المعمري. ناصر راشد الجامودي.
مازن سيف الحسني. Misna سيف الحسني. She's available or not? She's not available. Now الصوت المعمري.
ناصر راشد الجامودي. سعيد سيف الحبسي. مالك سعيد الشكيلي. فاطمة خليفة السناني. اسمه سلطان المعمري. مريم سلم العلوي.
كيف مان؟
عندنا شوي شهاده عندنا
مريم سلم العلوي. سعاد محمد الحدروشي. مسنة سليمان البحرزي. الريم علي العدوي.
ثريا العلوي.
العلوي.
الريم علي.
ثريا
موجوده بصراحه.
العربي.
الريم علي. وين؟ ثريا ما حد؟ الريم. أحمد عامر الصبحي. عامر حامد الخروصي. مصعب منصور الحسني. عزيز المحمودي، علي سالم الخصابي، موسى الصبحي، روان حسان، حميد سالم الشكيري، عمر حمدان الحوسني، عمر حمدان الحوسني، سالم عبد الله اللمكي، سالم عبد الله اللمكي، ناصر سيف المحفوظي، ماجد عبد الله، ماجد عبد الله المبيحسن، خالد سعيد الحارثي، المعتز أحمد المسروري، المؤثر سعود الناعمي، ناصر سيف. This is Khalid Hafi. ناصر سيف. سمارة السعدي. صفا أحمد الهلالي. منير خميس اليوسفي.
شيلكم معهم شوي.
مازن يحيى الحديدي. مازن يحيى الحديدي. منيرة محمد البلوشي.
طلع بالعدسة
الكاميرا
أحمد محمد الدهلي.
خلاص
مالك محمد النبهاني.
خلاص
خلاص هذا رجع
مالك محمد النبهاني. زملاء؟
هاي باين الصور
اوكي لا لا استنى خلاص. اوكي زملاء بعدين. طيب شكرا جزيلا لكم.